Friends, welcome to today's physics class, which is class 11th. Okay, physics class. Okay, fine. Today we are diving into a fascinating and a fundamental concept in physics, the conservation of mechanical energy. By the end of this session, you will be able to define mechanical, kinetic, and potential energy and understand and apply the law of conservation of mechanical energy, solve numerical problems related to it, and even identify real life example where this principle is at play. Okay, right. So before we jump into that topic, I want to share a short motivation story. So think about Galileo Galilei. He did not have fancy equipment, but through careful observation and simple experiments like dropping objects from the leaning tower of Pisa, he revolutionized our understanding of motion and gravity. Motion and gravity. His work laid a crucial groundwork for concepts like energy. It reminds us that perseverance and a curious mind can uncover profound scientific truths. So, just like Galileo, let's approach today's topic with curiosity and an open mind. Okay, all right. So, let's warm up our brains with a quick icebreaker quiz to recall some prior knowledge. I will share the link. Okay, once again. Okay, so this is the first question. Now you can see that one that is sensitive. What is the SI unit of energy? If you know the answer, please type in the box, chat box, or you can unmute yourself and tell that answer. What is the SI unit of energy? C1 joule. Good, good, sugar. Three. Yes, okay, joule. Very good, very good. A lot of responses. Okay, joule, joule. Okay, good. Four, Pascal. Okay, right. What is the SI unit of energy? Energy, joule. Very good, good. And the second question, which of the following is a form of energy due to an object's motion? Kinetic energy, yes, very good. Next, joule, okay. So for the previous one, okay, joule, very good. C, okay, 3, C, 3, okay, very good. Very good. 1, C, okay, 3, okay, right. So, which of the following is a form of energy due to object motion? Kinetic energy. Yes, very good. Well done. Yes, okay. The next one, very important one, that is, if an object is raised to a certain height, what type of energy does it primarily possess? It may be kinetic energy, it may be potential energy, or maybe electrical or sound energy. So, if an object is raised to a certain height, what type of energy does it primarily possess? For the third one, what is the answer? 3, 3, 1, potential energy, B, okay, B. B2 to B. Yes, very good, very good. Good. Government Junior College at the students. Yes, APM, Kerala, DJC, potential energy. Very good, super, very good. So, if the object rests to a certain height, the energy it is called as potential energy. Very good. So, let me check. Yes, what is the SI unit of energy? Joule. Very good. Which of the following is a form of energy due to the object motion? Kinetic energy. Very good. If an object rises to a certain height, what type of energy this flame will possess? Potential. Very good. Good. Great responses. Very good. Well done, students. Great. Okay. So, excellent. I see most of you have submitted correct responses. Okay. Next. Now, let's get into the core of today's session. Mechanical energy and then conservation. Okay. First, mechanical energy. So, mechanical energy is the energy of an object possessed due to its motion or its position. So, due to its motion or position, its position. Okay. Mechanical energy is the energy an object possesses due to its motion or its position. Okay. So, it is the sum of two types of energy. It is the sum of two types of energy. One, kinetic energy. And the next one, potential energy. First of all, kinetic energy. So, kinetic energy is the energy an object has due to its motion. Kinetic energy is the energy an object has due to its motion. Due to its motion. So, suppose if something is moving, it has kinetic energy. Suppose one ball moving, it has kinetic energy. Okay? Okay. We knew that the formula that is half mv square. Already we have studied in the earlier classes. Half mv square. Okay. Then next potential energy. Potential energy is the energy of an object has due to its position or state. State means nothing but position. Okay. So due to its position or state. Due to its position. For example, an object held above the ground. So this is ground. This is one object. So an object held high above the ground. It has this pen. Okay, this pen has gravitational potential energy because of its position, because of its height. So, what is the formula of potential energy? That is mgh. So here you can see that m, that is mass of that object. V, velocity of the object. Okay. Here g, acceleration due to gravity, and importantly height. H is be the height of the object from the ground. This is a very simple neat formula for that two type of energy. Okay. So mechanical energy is a summation of these two type of energy. Okay, good. Then next. Law of conservation of mechanical energy. First of all, we have to know what is mechanical energy, and then we have to move into the law of conservation of energy. Okay. So now, law of conservation of mechanical energy is the fundamental principle. Okay. It states that in an isolated system, so isolated system means ideal system, where only conservative force, only conservative forces do work. For example, here gravitational force is one of the great example for conservative forces. So only conservative forces do work. So the total mechanical energy, that is, you know that summation of kinetic energy and potential energy remains constant. Remains constant. So this is the definition for law of conservation of mechanical energy. In an isolated system, you can tell about that in an ideal system. So where in which that there is no external forces like air, resistance, or some other external forces. So in that isolated system or ideal system, there is only one type of conservative forces only there. So for example, in the gravitational force is one of the super example for conservative force. Okay. So this means that if we are not losing energy to things like air resistance or friction, total amount of energy in a system always the same. Even if it changes form between kinetic and the potential energy. So energy does not create nor be destroyed, but it can change into another form. Yes, kinetic into potential, potential into kinetic, and kinetic into thermal, like sound energy, light energy, this type of energy. So one type of energy can change into another form of energy. But in the whole view, there is no loss of conservation of loss of mechanical energy. That it means conservation. Conservation means always same, remains constant. This is a definition for law of conservation of mechanical energy. So suppose one object is there, it has kinetic energy and potential energy. So after the process, so after the hitting the ground or some other process, kinetic energy will change and potential energy will change, but in the view of total mechanical energy remains constant. That is, before kinetic energy and potential energy summation, and after potential energy kinetic energy summation will be equal. This is a fundamental basic thing related to this topic. Okay. So to really understand this concept, let's see it in action. We will use a fantastic simulation. I am going to start my screen now. I will open that FET energy scale for simulation. Okay. Right. I will share the screen. Okay. So here you can look at that one important fantastic simulation. Look at that our skateboarder. Yes, here as a skateboarder moves along the track, observe the energy bar here. Please observe here. So this is the energy bar. Okay. So whenever I am moving that skater, you can see that changes in the bar, energy bar. Is it correct? Okay. So when the skateboarder is at the highest point, what do you notice about the potential energy bar and what about the kinetic energy? You can tell via the chat box. So volume in my PC 100%, and actually I'm speaking with very loud. I don't know what thing. Okay, so please observe the potential energy bar and also the kinetic energy bar. What do you observe? What do you observe? Yes. Yeah. Okay. So yes. Okay. So at the peak of their path, their height is maximum. Yes, already we know that at the peak of their path, their height is maximum. So the potential energy is maximum. Okay. And they momentarily slow down. So kinetic energy is minimum. Okay. At the peak of the airport, the height is maximum. So potential energy maximum. At that instant, kinetic energy minimum or zero. Okay. Right. Now, as they go down into the dip, like dip. Okay. So what happens? Observe that potential energy graph and the kinetic energy graph. So potential energy decreases, kinetic energy increases. So at the bottom, kinetic energy maximum, potential energy zero. So as they lose height, potential energy converts into the kinetic energy and they speed up like this. Okay, right. So, and crucially, look at the total energy graph. You can now see the only total energy graph. So kinetic energy increases or decreases, potential energy increases or decreases because potential energy converted into kinetic energy converted into potential energy. Okay, good. Just look at the total energy ball. Yes, it remains constant throughout the motion. It remains constant throughout the motion. As long as we have kept friction off. Okay, as long as we have kept friction off. So this perfectly illustrates how energy transforms between potential and kinetic forms. But the total mechanical energy stays the same in an ideal system. Okay, clear? Is it clear? Okay, total energy is constant. Yes. The kinetic energy increases, potential energy decreases. Yes, very good, very good. Yes. So let me show you another simulation. Which has a screen now. Okay. Which is related to the conservation of mechanical energy. So here you can see that one building is at some height, it has some height that is 50 meter or 40 meter. At the bottom of the building, there is one ball. We can drop that ball from that position to the ground. So ball has something mass or 1 kg, 2 kg, something like that. Okay. So in the side screen, you can see that kinetic energy, potential energy, and total energy. And below, top position, middle position, bottom position, and the key principle, the total mechanical energy remains constant throughout the fall, demonstrate the conservation of energy. Okay. So at the top position, kinetic energy 0. Already we know that. Potential energy 490 joule. So which is mgh. Okay. Right. So total mechanical energy E is equal to 490 joule. Okay. In the middle position, something like that, half of the position h by 2, kinetic energy 245, potential energy 245. Then also total mechanical energy 490 joule. And that at the bottom position, totally potential energy 0 and the kinetic energy 490 joule. Like that. And the total mechanical energy 490. Okay. Right. Very good. Right. Now, so just drop the ball. You can see that the changes in the kinetic energy and potential energy, but always total energy equal, same as throughout the motion. So here energy analysis, you can please does not consider the energy analysis, just to consider this one. Okay, right. So this is the very simple demonstration for the conservation of mechanical energy. Okay. So here 490 joule means for the potential energy mgh, for the kinetic energy half mv square. We can put that value of the mass of the ball and velocity of the ball and the height of the ball from the ground. Okay, like that. Okay, right. Now, okay, right. So now that we have seen the concept visually. Yes, let's apply it to some numerical problems. Understanding this will help solidify your grasp of the construction law. I will solve two problems on the whiteboard. Okay. So problem number 1. A 2 kg ball is dropped from a height of 10 meters. Okay. What will be its speed just before it hits the ground? So take G is equal to 9.8 meter per second square. So this is a problem number 1. A 2 kg ball is dropped from a height of 10 meter. Already I told you, yes, the building height 10 meter and the ball at the top of that building. So the ball has something mass. So here 2 kg. So what will be its speed just before it hits the ground? Right? Okay. So already we know that law of conservation of energy. So by the law of conservation of energy, total energy before the process and the total energy after the process will be equal. That means potential energy of the ball initial and the kinetic energy of the ball in the initial position, which is equal to potential energy of the ball in the final condition or final position and the kinetic energy of the same ball. So potential energy plus kinetic energy, mechanical energy. So before the process and after the process. So here before the process means the ball dropped from the height. So that is a process. And then it hits the ground. So before the hits the ground, we have to find the velocity of the ball. Okay. So we knew that mgh and half mv square. Here also, so the ball has speed before, that is initial speed and the final speed. So I, and here also half mvf square. We have to find this speed, that is final speed, before that it's the ground. But the potential energy 0, because already you know that in that bottom position, potential energy of the ball will be 0. So we can put 0 here. Okay. And for this VI, so VI means initial speed of the ball. But in our problem, in this problem, the ball is at height. Yes, at the top of the building. So which is at rest. That means it does not have initial velocity. So we have to put 0 here also. So mgh plus 0, because 0 energy is 0. So 0 and 0 and plus half mvf square. Okay. mgh is equal to half mvf square. We can cancel the mass because same object. Okay. We can cancel the mass of the object from both sides. And 2 goes here because we have to find this term. So Vf square equal to 2 goes here. So 2gh. So then we have to find Vf. So take the roots. Because we have only Vf square. Vf square is equal to 2gh. To find the Vf, we have to take root on that side. So Vf is equal to root of 2gh. Now we will put the value of the g and the h here, and then we will get that answer for Vf, that is final velocity. That means the velocity of the ball or speed of the ball before it hits the ground. Okay. So Vf equal to root of 2GH. Just put that value. 2 into G, 9.8 and H. So here 10 meter height, so 10. You can multiply that. So 9.8 into 10, 98 and into 2, 196. Yes, 14.14. Very good, very good, great. So 196. So we can take that root value of 196. So we can take 40 meter per second. So this is the speed of the ball before it hits the ground. So the ball's speed just before hitting the ground is 40 meters per second. Notice how the initial potential energy was completely converted into kinetic energy. Okay, initial potential energy was completely converted into kinetic energy. Okay, okay. We will solve another one problem, which is problem number 2. Problem number 2. A 0.5 kg block of block slide down a frictionless incline from a height of 5 meters. What it is, okay. What is its kinetic energy when it reaches the bottom of the incline. This one problem, which is another problem which is very important. So here also we can assume that G is equal to 9.8 meter per second square. So just look at this problem. Yeah, 0.5 kg block slide down a frictionless incline from a height of 5 meters. What is its kinetic energy when it reaches the bottom of the incline? Okay, I will draw the simple diagram related to this problem. For example, so this is a horizontal, this is the inclined surface. So this is the frictionless surface. Here one block. So this is slide down here. So from the this is height of that position, height of that building, height of that like that ball position. Okay, from the ground level. Okay, right. So it is a bottom. So here you can see the bottom. So the block slide down on the frictionless surface and then hitting the bottom here. We have to find the kinetic energy when it reaches the bottom of the incline. Okay, fine. So at top position, that is initial position, initial state, kinetic energy 0. Yes, at some height, potential energy will be maximum, kinetic energy will be 0. So at top, initial state, at the initial state, kinetic energy 0, potential energy maximum. So which is mgh. Okay. So just to put that value for m 0.5, g 9.8 H5. We will get that 24.5 joule. Okay. So now at the bottom position. So this is a final state. At bottom position means final state. So in the final state, potential energy will be 0. Kinetic energy, we have to find. What is the value of kinetic energy? We have to find. Okay. So by the conservation of mechanical energy, kinetic energy initial plus potential energy initial equal to summation of kinetic energy final and the potential energy. Summation of kinetic energy of the final state and the potential energy of the final state. Okay. So KEI 0. PEI 24.5. So 24.5 joule. KEF, we have to find this term KEF. So potential energy final 0. Okay, like that. So then answer kinetic energy in the final state. (24.5 joule). So this is a kinetic energy of the ball of the block when it reaches the bottom of that incline. Okay. So here, because the incline is frictionless, all the potential energy is transferred into kinetic energy at the bottom. So that incline is frictionless. So all the potential energy at the initial position. So okay, all the initial potential energy is transferred into kinetic energy at the bottom. The kinetic energy when it reaches the bottom is 24.5 joules. Okay. So great work on those problems. Okay. Now it is time for short quiz to check your understanding of today's concepts. This is a 5-question MCQ quiz on the conservation of mechanical energy. Okay, I will share the link. So, okay. First question. The sum of kinetic energy and potential energy is called. If you know the answer, yes. 2, 2, 2, 1. Okay. Mechanical energy, yes. B, 1, A, P, F, must B. Okay. 2. Okay. Okay. Very good. 2B, 2B, 2B. Okay. Okay. Right. Good. The sum of the kinetic energy and the potential is called, yes, mechanical field. Okay. Good. Great. Great. Very good. The next question. According to law of conservation of mechanical energy, if only conservative forces are doing what? The total mechanical energy of the system increases or decreases, remains constant, becomes 0. For the second question, 2B, okay, B, okay. Linear down, SL, or students, yes. GGB, Saturn, GGC, Parvati from, okay, good. Boys, okay, APGL, boys. 3, 3, 2, 2, 0, okay, C, oh, remains constant, yes, okay, right, very good. Very good responses. So according to the law of conservation of mechanical energy, if only conservative forces are doing work, the total mechanical energy of the system remains constant. Good, great, very good. Okay, we will move to the next question. Third question. A ball is thrown vertically upwards, neglecting a resistance. At its highest point, its kinetic energy is maximum, minimum, but not zero. Zero equal to its potential energy. For the third question, what is the answer? KGB equal 3, 1 equal to 3, AB, 0, 3, 3, 0, 0, 3, Z. Okay, lot of various responses from that product. Very good. Various options there. So it may be maximum, minimum, 0, equal to its potential at its highest point. Yes, 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 very good. So at its highest point, kinetic energy 0. Okay, so that is one type of energy is available in that position. That means that is known as, already we know that, potential energy. Yeah, good. This is girls. Okay, very good. Super. Then next one, fourth one. A pendulum swing back and forth. At the lowest point of the swing, which type of energy is maximum? Just think about it. This time we need to B, 2, 1, kinetic energy. Okay, kinetic 1, 1. Okay, okay, right. 3, 2, lot of questions. Okay, Anamaya. Okay, okay, 1. Okay, boys, maybe just by both 2 and 3. Okay, good. Both 2 and 3. Okay. We are investment. This is just 2 students, 2. Okay, okay. Kinetic energy. I think, okay, right. Okay, good. Very happy to see that. A pendulum swings back and forth. At the lowest point of the swing, kinetic energy, potential energy, both kinetic and potential energy equally maximum thermal energy. So thermal energy will be available when in the case of ground level. Yes. Now suppose if the object hits the ground in that not in the ideal situation, not in the closed system, not in the conservative system. So in that open system. So when that object or when the ball hits the ground, its temperature will rise. Okay, a little bit. Okay, so we can measure the special type of thermometer. By using the thermometer, we can see the little bit temperature variation in the case of open system. Okay, so here pendulum does not hit the ground, so pendulum just swings back and forth. So there is no possibility of thermal energy here. Okay, good. Then next one, both kinetic and potential energy are equally maximum. Does not happen. Yes. Okay. So potential energy maximum. In that case, kinetic energy is 0. So kinetic energy maximum. In that case, potential energy is 0. Yes. Okay. So the speed depends upon kinetic energy. Yes. Because already we know that kinetic energy of mv square and potential energy mgh. So at the bottom, at the lowest position, there is no height for mgh. So here h is equal to 0. You can put that 0 in the value. So there is no potential energy. Only one type of energy is maximum, that is okay. Kinetic energy. Very good. Good. Second one. Yes, yes, yes. Okay, okay, good. Okay, we will move into the next question. That is last question. A free falling object neglecting. Oh, okay. A free falling object neglecting a resistance has its maximum kinetic energy. Very important question. A free falling object neglecting a resistance has its maximum energy at the beginning of the fall, at the halfway point of its fall, just before it hits the ground, or it remains constant throughout the fall. 2, 2, 3, 3, A. Okay, okay. Down 3, 2. Okay, okay, 2, 3. Okay, okay. Right. Just before it gets one down. Okay, very good. Follow from 3, junior college 3, 1. All the students can leave. Okay. Vote for the poll immediately. Yes, yes, sir. 3C just before it reaches the ground. Oh, good, good. 3C, 3C. Okay, good, good, good. Okay. So already we have done one problem related to the topic. Yes. So a free falling object, including air is maximum kinetic energy just before it's the ground. Yes. Okay. So submit. So we can see the answer. The sum of the kinetic energy potential is called mechanical energy. According to the law of conservation of mechanical energy, if only consider doing work, total mechanical energy of the system remains constant. A ball is thrown vertically upwards, neglecting direction. At its highest point, its kinetic energy is zero. Good. A pendulum swings back and forth the lowest point of the swing, which type of energy maximum? Yes, kinetic energy. And then final one, a free falling object neglecting direction has its maximum kinetic energy just before it hits the ground. Very good. Students, very good. Super. Great work. Excellent. Excellent. Very good. Very good. Okay. Right. So we have covered a lot today. Let's make it interactive now. Can 2, 3 students share a real life example where mechanical energy is conserved or transformed? And for your example, try to identify where kinetic energy maximum or minimum and potential energy is maximum or minimum. Think about like things like a roller coaster, bouncing ball, or even a thing. Okay. So, any students, anybody share a real life example related to this mechanical energy, or you can say that identify where the kinetic energy is maximum or minimum. Just think about a roller coaster, bouncing ball, swing, and identify that highest point and the lowest point. Okay, nice. So now, before we wrap up, do you have any question about mechanical energy, kinetic energy, potential energy, or the conservation law? Do you have any question related to this topic? If you have any question or if you have any doubt, you can ask me. You can type in the chat box. Okay. Okay. There is no questions there. Okay. All right. Let's quickly summarize what we learned today. Okay. First of all, mechanical energy. So mechanical energy is the sum of the kinetic and the potential energy. Kinetic energy is due to the motion. Potential energy is due to the position. Clear? And the law of conservation of mechanical energy states that in an isolated system with only conservative forces that are there, the total mechanical energy remains constant. We saw how this principle applies to energy transformation and how to use it to solve numerical problems. Yes? Okay. For your homework, I am assigning two problems that will help you practice these concepts. I will write. Please take down. This is your for your homework. First question. A roller coaster car with a mass of 500 kilogram starts from rest at the top of a hill. So 25 meters high. Assuming no friction. Assuming no friction. What is its speed when it reaches the bottom of the hill? So take G is equal to 9.8 meter per second square. So this is a first problem for your homework. I will write the second problem later. A roller coaster car with a mass of 500 kilogram start from rest at the top of the hill to 25 meters height, assuming no friction. Okay, so here what yes please put okay student, thank you for your responses. Okay, good, thank you so much. Okay, good. So what is its speed when it reaches the bottom of the hill? Thank you, AB, RJ boys. Thank you. Okay. So take G is equal to 9.8 meter per second. So this is the first problem for your homework. Please write it down. I will write the second problem now. Okay. Okay. Right. Thank you. So second problem. So it is a type of activity like homework. Explain how the principle of conservation of mechanical energy applies to a child on a swing. Describe the energy transformation that occur during one complete oscillation of the swing. So this is the second one. Explain how the principle of conservation of mechanical energy applies to a child on a swing. Okay. Describe the energy transformation. Kinetic energy to potential energy to kinetic energy. Okay. That occur during one complete. So just think about one complete. What do you mean by one complete oscillation in that swing case? Okay. During one complete oscillation of the swing, just imagine how the energy transfer between those type of energy variations. Okay. Thank you. Yes, thank you. Very good. Thank you. Very good. 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 Thank you. Sir. Thank you. Very good. Super student. Very good. Thank you. Very much. Always exploring the world with the scientific eye, not by the normal eye, scientific eye. So this is very important to our life. Thank you. Yes. So all the schools kindly vote for the poll immediately, please. Please, all the schools kindly vote for the poll. That is class feedback. Already you know that. Yes. You can choose any one, but just vote. Okay. Jai Bharat, Jai Hind, Jai Vidyasri. Thank you.